Welcome to the third and final video of Topic 6. In the previous video, we derived integral expressions for the coefficients in a Laurent series. But in practice, manipulation of known geometric and Taylor series is usually an easier way of finding these coefficients. In this final video, we're going to work through a few examples of finding Laurent series using these methods. As a quick recap of what we did in the previous video, we derived Laurent series for a function in an annulus of analyticity, where the ring of interest circles around some region of non-analyticity. And we also understood the different regions of convergence for positive and negative powers in a Laurent series. These are the intended learning outcomes for this video. After watching this video, you should be able to find the Laurent series for complex functions about different expansion points, and generally you'll do that using known Taylor or geometric series. You should also be able to appreciate that different regions of the complex plane need different Laurent series. In other words, the coefficients of the Laurent series can be different in different regions. As always, after watching this final video, I encourage you to have a go at the questions in the problem sheet to test your understanding of all that we've covered. And with that, let's start this last video of Topic 6.
In this video, we're going to look at how to find Laurent series. In the previous video, we saw how to express functions that are analytic on an annulus using Laurent series. Now we'll go through some examples of how to find them. From the previous video, we had that you can express a complex function as a sum from n equals minus infinity to infinity of some coefficients times z minus z naught to the n, where z naught is the expansion point, n is a natural number, and this expansion was valid for z minus z naught lying between little r, which is the minimum radius of analyticity, and big R, which was the maximum radius. And you'll also recall that we derived the expression for these coefficients as 1 over 2 pi I, the integral around a circular contour that lies in that annulus of analyticity, f of w over w minus z naught to the n plus 1 dw. This expression looks a bit messy, and in fact it's typically not very practical to use the integral expressions, but there is an easier way to find the Laurent series nevertheless. I'll write this down. Often it's not practical to use the integral expressions to find the coefficients an. The way that we're going to demonstrate in this video is instead, it's usually easier to manipulate known Taylor or geometric series. Into a suitable power series with positive and negative powers that converges in the desired region. Okay, so it's usually easier to manipulate known, Taylor, or geometric series into a suitable power series with positive and negative powers of n that converges in the desired region. I'll also note that it doesn't really matter which of these approaches you use, whether you use the integral expressions or you spot an appropriate geometric series. The approach doesn't matter. And that's because it can be shown that Laurent series are unique. And in fact, I think there's a quick proof on the Wikipedia page for Laurent series. This means that once you've found a Laurent expansion, you know it's the expansion that you would get any other way. Right, let's get started on some examples. First of all, let's consider expanding the function f of z is 1 over z minus 1 squared about the point z0 equals 1. You can see that this function is singular at z0 equals 1. It blows up and there are no derivatives to find there. In fact, we're already done. This is the Laurent series. It's in the appropriate form where we know that we're looking for something like this. Writing that out, we have something like a minus 2 over z minus z0 squared plus a minus 1 over z minus z0, a constant term, and then ascending powers, and so on. So we can see, as written, we've already got the Laurent series. The coefficients, the only non-zero one is a minus 2, which is given by 1. All the other coefficients are 0 for n does not equal minus 2. And this expansion is valid for any z minus 1 that is greater than 0. So that was quite a trivial example. The next example, we'll see how we can use Taylor series. Let's consider expanding f of z is e to the z over z squared about the point z0 equals 0. Once again, we can confirm that this function is singular at the chosen expansion point. And the way we're going to approach this is we're going to substitute in the Taylor series for e to the z. You'll recall that that is the sum from n equals 0 to infinity of z to the n over n factorial. You'll also recall that this is valid for all z. And that's because the exponential function is an entire function. Right, therefore, we have that e to the z over z squared. Well, that's just going to be the sum from n equals 0 to infinity of z to the n minus 2 over n factorial. We can write that out quite straightforwardly. The lowest term is going to be 1 over z squared. We'll have a 1 over z, a constant term of 1 over 2 factorial, and then the first positive power over 3 factorial, z squared over 4 factorial, and so on. I'll write down that a minus 2 and a minus 1 coefficients, those are 1, and an, this expression is for any n greater than or equal to 0. And we're done. This is our Laurent series. And this is valid for all z greater than 0. These two examples have been relatively straightforward. The next one's a little bit more complicated. For our third example, let's consider expanding f of z is 1 over z 1 plus z squared. And let's consider expanding that about z naught equals 0. You'll spot that the denominator is 0 for z equals 0, or if z squared plus 1 equals 0. So the other solutions are when z equals plus or minus I. We can therefore draw a picture to see what's going on. We have our real and imaginary axes. We have a singularity at the origin. We have another singularity at plus I, and a third singularity at minus I. I'm going to draw a circle, and it'll become clear why in a second. We can treat the regions both inside and outside the circle as annular regions, similar to the ones that we saw in the previous video when deriving Laurent series. I'm going to denote the region inside this circle as region A, where the absolute value of z lies between 0 and 1, and another region, B, which is everything outside that circle, that unit circle, and this is where the absolute value of z is greater than 1. We note that the Laurent series conditions and by that I mean our condition of an annulus of analyticity. These conditions are met for two different regions. Which I've labelled A and B above. In both those cases, the expansion point can be taken as 0, but we'll see that there will be two different expansions. So there will be a distinct expansion for each region. Right, let's begin with region A, where z lies between 0 and 1. Well, we have f of z is 1 over z times 1 over 1 plus z squared. And you might recognise this second term, 1 over 1 plus z squared, as a convergent geometric series. Substituting that in, this is the sum from n equals 0 to infinity of minus z squared to the n. And you can check for yourself using the ratio test that this geometric series converges in the region that we're interested in. We can multiply that out to have 1 minus z squared plus z to the 4 minus z to the 6, and so on. And this therefore gives us 1 over z minus z plus z cubed minus z to the 5, z to the 5, and so on. Therefore, we found that in region A, our function can be written as the sum from n equals 0 to infinity minus 1 to the n and z to the 2n minus 1. You can check for yourself that these expressions are equivalent. We can also write this in terms of the coefficients an. We have that a 2n minus 1 equals minus 1 to the n for all n greater than or equal to 0, and all other coefficients are 0. Okay, so that's our Laurent expansion for our function in the first annular region. The other region, region B, has that the absolute value of z is greater than 1. So that's the region outside that green circle above. That's also an annulus with inner radius 1 and outer radius tending to infinity. Compared to what we did above, we're going to have to manipulate to get a convergent series as before, about z naught equals 0, the origin, but looking for terms in 1 over z. And that's to stop our power series diverging as z increases. We have, as above, f of z is 1 over z times 1 over 1 plus z squared. Now we can manipulate this second bit by taking out a factor of z squared, and inside this bracket having 1 plus 1 over z squared. Taking factors together, we have 1 over z cubed times 1 over 1 plus 1 over z squared. And just as we did above at the top of the page, we recognise this second term as another geometric series, but this time in powers of minus 1 over z squared. This is therefore 1 over z cubed times the sum from n equals 0 to infinity of minus 1 over z squared to the n. And you can check for yourselves that this converges for mod of z is greater than 1. This is looking good. We can multiply this out to see specifically what's going on with the coefficients. So we have 1 minus 1 over z squared plus 1 over z to the 4 minus 1 over z to the 6, and so on. Minus 1 over z to the 5 plus 1 over z to the 7 minus 1 over z to the 9, and so on. Therefore, we have that in region B, our function f of z is given by the sum from n equals 0 to infinity of minus 1 to the n, and then we only have negative powers of z. We've insisted that n is positive, but all of the powers of z are negative. And this series here will converge in region B. All of the powers are in 1 over z. We can write this in coefficient form, that a minus 2n minus 3 are given by minus 1 to the n for n greater than or equal to 0, and all others are 0. I'll end this example with the note that even though we're expanding for mod z is greater than 1 in this second region, the expansion is still being taken about z0 equals 0. As one more example, fourth example, let's consider expanding f of z is 1 over z times z minus 2 squared about the point z0 equals 2. Let's draw a picture. We have real, imaginary. We have singularities at the origin and also at plus 2, where the denominator equals 0. Once again, I'll draw a circle, this time centered on the expansion point at plus 2. Now, how do we approach this? Well, we want to do an expansion about the point z0 equals 2. So it's going to be helpful to define epsilon equal to z minus 2. And then look for expansions in powers of this number, this complex number, epsilon. We can now write our function in terms of epsilon. It's going to be 1 over 2 plus epsilon times epsilon squared. We can rewrite this as 1 over epsilon squared, and then if we take out a factor of 2 on the denominator, we have 2 lots of 1 plus epsilon over 2. As before, you can spot that this second term on the right hand side is a convergent power series, this time in the variable minus epsilon over 2. Taking this factor of 2 out the front, we then have the sum from n equals 0 to infinity of minus epsilon over 2 to the power of n. We can multiply this out to have a look at the first few terms. This is going to give us 1 minus epsilon over 2 plus epsilon squared over 4 minus epsilon cubed over 8 plus epsilon 4 over 16, and so on. Multiplying this out, the first term is this. The second term is going to give us 1 over 4 epsilon. We'll then have 1/8, then minus epsilon over 16 plus epsilon squared over 32, and so on. We're now in a position to substitute back in that epsilon is z minus 2, and we obtain 1 over 2 z minus 2 squared minus 1 over 4 z minus 2 plus 1/8, and then we have the positive powers z minus 2 over 16 z minus 2 squared over 32, and so on. And I'm not going to bother writing down the explicit formulae for the coefficients, but you can do it yourself if you want. And this expansion is valid for z minus 2 is between 0 and 2, which is clear from the green circle at the top of the page. As practice, you can also consider expanding this function about the other singular point, z0 equals 0. That's it for the examples of finding Laurent series. I'm going to end with a little hint about why we're going to care about Laurent series when performing contour integrals. So, spoiler alert. You'll recall that these coefficients an are given by 1 over 2 pi I. The integral along a closed contour C in the annulus of analyticity of f of w over w minus z0 to the n plus 1 dw. It's easy to see that the coefficient for n equals minus 1, well, the denominator becomes unity. This is simply the integral around a closed contour C of the function f, and this is a contour integral that may enclose singularities of our complex function. You can also note from our earlier discussion in the third example that this coefficient a minus 1 can be different in different regions. We had that the coefficient equals 1 for z lying between 0 and 1, and it equals 0 when the modulus of z was greater than 1. To end this topic, I'll write that we'll see the importance of this quantity, which is called the residue, in the next topics. That's the end of this third video of topic 6. As a recap of the entire topic, we derived the generalised Cauchy integral formula that showed that you can find the value of a complex analytic function and its derivatives at a point using values of the function on a contour enclosing the point of interest. We then used this to find Taylor series for complex functions that are analytic within a circular region, and we define the radius of convergence for such series. We then derived Laurent series, and these were power series in positive and negative powers of z minus z0. This allowed us to expand complex functions in an annulus of analyticity, i.e. about some singularity. And in this last video we looked at some examples, and we saw that the coefficients of your Laurent series depend on the region you're expanding in. We'll see the relevance for contour integrals in the next topic. As usual, I encourage you to have a go at the problems in the associated problem sheet to test your understanding of everything that's been covered. There's also some additional content on the Blackboard page for this topic, and that goes through the answers to one of the questions on the problem sheet and should give you a picture of what's going on when you construct a Laurent series. And with that, that's the end of topic 6. Thanks for listening.